Hey guys, my name is Akshul Agarwal, and I'm going to take you through my presentation for the final term project of the machine learning course. I've made a small PowerPoint presentation as well for this, so I'm going to keep toggling between my R code and my PowerPoint presentation. I'll keep pausing the screen recording in between, so it doesn't take too much of our time to while I'm talking between the two. And yeah, so let's get started. And I'm gonna start off with my PPT presentation with a couple of slides, and then we move on to the R code, and I'm going to explain you what each and every line does. All right, yeah. So yeah, I call my project Prudential Life Insurance because that is the data set call which I've taken from Kaggle, and I'm just going to highlight what the project goals here are, and how I'm performing the important data analysis before we move on to the R cleaning part, and also move on to the R notebook file, right? So yeah, these are the project goals. So the objective here is to basically develop a predictive model for risk classification and calculating eligibility of a particular individual, given we have the client data, and such as the medical history of the client, which has a lot of a lot of different values, product history and whatnot. The risk level here helps the Prudential Life Insurance Company provide an exact code of life for each insurance and for each individual. Again, this is just the same thing. We have a bunch of data given 127 columns to be precise. This is the client data that we have, and based on this data we need to predict, okay, what's a client's eligibility for a particular insurance, and this data is for 58,000 individuals. I'm going to talk about it in the next slides. Yes. So yeah, exploratory data analysis. So our database, as I said, has 127 independent variables, which are the different factors or features on which, using which we are going to determine our one dependent variable, which is also called the response variable. And we have about more than 58,000 records, which means those are the number of patients or clients that we have. And all these features, they're either continuous, categorical, or discrete in nature. We've been given what columns are continuous, categorical, and discrete in nature, and accordingly we've made changes to the data so that it better fits our predictive model, and we've cleaned it accordingly. So as I said, the response field in the data set is our dependent variable. We're trying to go predict this using the 127 other variables, and the value for this response field could range from 1 to 8, where 8 is the highest level of risk and 1 is the least level of risk. So the company Prudential Life Insurance will have the risk associated with each individual, where 8 is the highest level of risk and 1 is the least level of risk, and accordingly they could give out an insurance code for each individual. For an individual with the least amount of risk, they would have somebody with low premium and probably a higher coverage, because they know, okay, this person is the risk of this person getting sick or claiming the insurance eventually is low. Whereas if a person has a risk level of 8, the premium is going to be high and the coverage is going to be a little on the lower side, because they know, okay, the risk associated with this particular individual is pretty high. I'm going to move on to the R code now. So yeah, here is my R code. We first start off by cleaning the data. We first actually start off by reading the data and performing wrangling functions on it so that it's made usable for analysis. So I'm just gonna quickly go over this because I see I've already taken 4 minutes and the presentation should not exceed 10 minutes. So here I have no, here I have the link from where the data set has been extracted. I am reading the data here into a potential data file, and as I said, we've been given what columns are categorical, what columns are discrete in nature, and what columns are continuous in nature. So we're gonna start off by separating these variables according to their nature, such as categorical, discrete, and continuous. So what we do here is we make a new variable or a new vector called cat names, wherein we post all the categorical columns such as product info 1, 2, 3, product info 567, employment info 235, insure info 127, insure history 12434, 789, and so on. We're doing the same here for our discrete columns. We have the column names, such we've given it a value called disk names, and we have all the column names here, which are discrete in nature. We're doing the same here for continuous columns, right? Yeah. So once we have these column names, we put them in another vector called prudential.cat. Cat here stands for category, categorical. Cont stands for continuous, and disk stands for discrete. So we have another data frame, prudential, which we basically subset our original data frame into a new data frame with only these column names for all the three different categories of columns data, such as categorical, continuous, and discrete. And yeah, so this is where we come to a cleaning part, right? So what my understanding here is columns which have more than 50% or 60% missing values, we're just going to eliminate them, because for I believe such a huge amount of missing values, they cannot be used for analysis. So we take care of so and so columns, column number 3, 4, 5, 6, which have humongous amount of missing values. Now you'll ask me, how did I come to know about missing values? Yeah, so we could just find the total. We had the total number of records, and for every column I found what were the total number of missing values, and just found the ratio of the two, and whichever had more than 60%, I just eliminated them. So here we're doing this for the discrete and continuous. And coming back to the categorical, we are removing columns which have more categories than 6, because in our analysis for the project, if we have such a huge amount of number of categories, it's going to prove difficult for our analysis, and so we're limiting ourselves to only 6 categories per column. And so any column exceeding that amount of categories are just eliminated to make it easier for us for me in the future for the analysis purpose. And as I said, this is all a part of our data wrangling. And as we see, okay, I will show you the Excel data set in a few moments. So as we see, a lot of values are missing, right? So how do we impute those values? We could have used the mice package, but what I did was I just found out the means for those for the entire column, and I imputed the values. So as I can see, is.na. Okay, if it's na, we just find the mean of that particular column, and where it's na.rm equal to true, we just impute it. We're doing this for the continuous variables, and coming to discrete variables. Again, that's the format followed. Just imputing using the mean function, right? So now what we're doing here is we're performing a 1-to-C transformation. So we have values which range from probably AA to some another value from 1 to some high number of value. But basically we want our values to be limited to be in a 1 to 1 0 variable type of format, so it's easier for us to perform our analysis later, since we cannot really take values which column which has a value 1 and which has a value, let's say 998 or something like that, right? So using this function package called ADE4 and the function called ACM disjoint CIF, I'm performing this analysis. So what it does is basically expands all our values into a 1-0 indicator variable for every factor level. Yeah, I'm going to run this code and show you the output later, but right now I'm just moving on with the code. So we've created a new data frame dfcat data frame category to perform this 1-to-C transformation, and our response variable is untouched. We want to keep it as what it is, so it's put into a different vector. And then once the 1-to-C transformation is done, and we make a new data set called dfcat1, which has the transformed 55 columns and our response column bind together. And now what we do here is, so as I said, the 1-to-C transformation was for the continuous variables, and we had already wrangled our categorical this was for the categorical variables, and we had already wrangled our data for the continuous and the discrete variables, right? So now I'm gonna make a new data set and bind our continuous variables, our discrete variables, and our categorical variables all wrangled. And now we're gonna have a new data set on which we're gonna perform analysis called PRUD. I'm just gonna write this data set into a train data1.csv file, which will make it easier for me to go back later and check out its values. Now, performing dimension reduction using linear regression. So as I said, I wrote this file back into my machine. I'm gonna read it again. This is my train data one, and I'm just gonna perform a regression on it and see if I could actually cut out some values and make my data set even smaller. So I've performed regression on it. I'm finding the summary, and what I'm doing here is I'm taking only those values which have p-value, which have significant p-value, significantly less low p-value, so that they give us they prove useful for our analysis. We don't want columns or data where the p-value is let's say 0 0.7, 0 0.81, or with higher p-values relatively. So this is what I've done. This was manual. I looked at all the p-values and I just took those columns, and I just binded my response variable to this new data set called prod1, which is after the dimension reduction. And I'm just doing performing another regression on the new data set called prod res, and checking to see if we can reduce some more values and make our data set probably smaller. And we did this, and we make another data set called prod2, which is after two dimension reductions, and we add our response column to it. And yeah, I think we're done here, because if we perform any more dimension reduction, we see that the multiple r squared value starts decreasing rapidly. And I think, so I just stopped it here, and I believe we have our data cleaned and ready to be analyzed, and no more dimension reduction is required here. So as I did previously, I'm just going to write it to my machine into a file called final data. So this is a final clean data. And now comes the most important part, right? I mean, we have a final data. We just have to divide it into testing and training parts. So using the sample function, these are the total number of rows that we have. We're just going to divide into so many different samples. And here we go. So that's our final testing data, and that's our final training data. I'm just going to run the R code now and pause the screen and just show all the outputs. Hi guys, so my R code worked, and these are all the outputs that I'm getting. I could go through it, but it's just gonna take a lot of time, and I've already exceeded my time of 10 minutes, so I'm just gonna rush through this. And so I'm just gonna move on to so I'm making use of four models: multiple linear regression, which will use a lasso regression and a normal linear regression. Then I'm gonna do these decision trees, and then I'm gonna do SVM, and finally XGBoost, and compare their which one's the best using the RMSU values. So the first one is going to be the for linear regression. So this is a train data, final train data. This is a test data. We're reading it again. I've explained to you how we got to our final training and our final testing data, and now we're just fitting our data using a train data, and then we find its summary. And once we have a fit data, we use this data to finally predict our response variable, which is a 55th column. So that's why I'm using -55, so that it does not include the summary response variable with it. Then we just find the summary, so that we have the RMSE value. We're gonna plot it for understanding, and then this is what. So we're just gonna plot it so that we understand it better visually. Now we combine both the actual response and the predicted response, so to find the RMSE value, right? So this is what we're doing here. And then to find the RMSE value, we just take there's a formula for it, mean, and then minus the prediction square, and then we just get up RMSE value. And another plot of the fit data to visually see what's happening behind the scenes, and how the data points are plotted and whatnot. The second regression that I'm doing here is lasso regression. So we need to have our package is installed for is called JLMnet, and I'm gonna put everything in a matrix. I'm gonna put my data in a matrix except for the response variable, which again comes from the train data, and my I'm gonna put my response variable in a vector called y, and then I'm just gonna perform some calculations on it, which is we need to do this for the lasso regression. I'm gonna use alpha value equal to 1 and lambda equal to grid. These are again default values you could use. You could just change values and go with it and find whichever fits your model the best. We find the summary. This is again, we've done this. Again, we need to first find the fit data for lasso, so we do this. We find the fit lasso data working on a trained data set. We plot it, and then we perform prediction on it, right? So using the predict function. So fit lasso is here. We're using a test data, not excluding the response variable, which is going to round it off, find the summary, plot it, find the RMSE value. So I'm just quickly going to run the R code and pause the recording and resume it again. Hi. So as we see, this is the RMSE value we're getting for the linear regression, and sorry, which is 2.08 something. Yeah, 2.8087, and the RMSE value for the lasso is 2.109. So not too bad, not too far away from each other. As we predicted, these are the various graphs that we've plotted. So now I'm just going to talk quickly about decision tree regression that I'm doing here. So first thing, we need to install our packages, have it in our library. As I said, we have a training and a testing data set. Now what we do here is we first create a tree using the R part, okay, and using a training data method equal to ANOVA. This is what I'm using. There are different methods that one can use, but I'm using ANOVA method. And I'm using PRP function on my tree. Basically, what this function gives me is it scales down this tree for me, and it gives me a best fit. So this is a very important step for a decision tree regression. Then we need to plot a tree and find out the R square and error for the tree. And so once we find out the R square error, we get different CP values. So I select the CP value with the least error, which is going to help me probably get the best fitting model for my decision tree analysis. So I'm again using the prune function on my tree with the least CP value to avoid overfitting, basically. Again, performing PRP on my prune tree, on my new tree. PRP, again, as I said, it scales, it gives you a best fitting tree, it scales down the tree. And yeah, so now what we do is we predict the data using the predict function. We're using a prune tree, which is a scaled down best fitted version of our tree, using the testing data, and type here is vector. And the test data response is put into predict data. And this, I'm just reading this file back from my machine. It's not really needed here. And finally, again, we just calculate RMSE so that we could compare it with the other RMSE values with the other models and see which one works best with our data set. So for the decision tree, as we see here, we get an RMSE value of 2.2. Not too bad, but the regression worked better if you look at the RMSE values. These are the graphs for the trees that I've created, and we could take a look at them later. So now we move on to the SVM regression. So again, you need these libraries. The packages are installed already, so I'm not going to do that again. I read the data from my training data set. I perform a subset which does not include my BMI column. Then I read my testing data set, again subsetting it, excluding the BMI column. And this is just to find out the structure of the data set for both data testing and training data set. So now what I'm going to do here is I'm going to make a sample of so many columns, so many rows with 1,000 sample size and equal to 1,000. And I'm going to put this sample index into a train data set. And using that train, I'm gonna perform my SVM regression. So for my SVM regression here, the kernel I'm using is Radial. I would have loved to use different kernels, but yeah, like that's in my future scope of work. I would try and use different kernels and see which is the best fitting one for my data set and for my model. But for now, I'm using kernel equal to Radial. So I'm just gonna tune my data set and then find out the summary for this, print it out here, and then I'm going to apply my SVM on my tune data set or my summary RAD, which I'm finding out here. And again, I've used cost equal to n and gamma equal to zero point 0.5 to build a SVM model. These are again values. You could use default values. You could use your own values to see which one fits your model the best. I believe this one fit my model the best, so that's why I'm using this. And then just gonna print it out, and in the end, I'm just gonna predict it using my fit variable. I'm going to predict my response variables, and then as done earlier, I'm just going to print out my RMSE and see how it performs compared to the other. So while I run this hard code, I'm just going to pause the screen recording, and then later we're going to see RMSE value for SVM, and then we move on to XGBoost, and then I just go through my PowerPoint presentation and we conclude this. So while my SVM is still running, I'm just going to walk through the XGBoost model and then go to the PowerPoint, and hopefully the SVM is run by then. So for the XGBoost, yeah, these are the packages you need to install, and then the same mode, you read the trailing data, the test data, and so you need to create another vector which would hold your response variable or the dependent variable, the one that you want to predict. So this is what I'm doing here, and then you create a subset using a data where you have wherein you have all the columns except for the dependent variable, the variable you're trying to predict, which is the response variable, which we're doing here. So those are the predictors, and yeah, that's it. I mean, then you just apply the XGBoost, and there are a few parameters that you need to change. Again, as with all the other models, these are completely up to you. You could just start off with some values and then probably move ahead or in the opposite direction depending on which is the best fit for your model. So here I'm just keeping maxed at 4 and round equal to 20. I tried a couple of different numbers, but they didn't work out too well. I mean, their RMSE values were a little higher, so this I believe is the best fitting for my model. And then you predict using your fit data and your test set, and then you just get your RMSE, which we get here is 2.032806, which along with the linear regression is the best value, the least RMSE value that we're getting. So the conclusion here is XGBoost and linear regression, they fit the model the best, and still waiting on SVM to run. And in the meantime, I'm just going to take you through the PowerPoint presentation, and then hopefully we have the SVM RMS value as well. Yeah, so I guess this is where we stop. Yeah, so moving on, this is just a graph of all the predictive variables. You can see product info, age, whether these are continuous or categorical variables, discrete variables. These are the risk levels, and count for each of the levels. As I said, we have 1 2 3 4 5 6 7 8 values for the risk column, or the column that we're trying to predict, and these are the count for each. This is basically, as I explained, what I'm doing in data cleaning. And as I said, dimensions containing more than 60% values are removed altogether. More than 6 categories are removed. We impute the values using mean. Then we perform a one to C transformation. We perform dimensional reduction and take values, which is with p less than 0.05. Then we move on to a first model, which is linear regression. This is just a snippet from the R code. This is one of the graphs. And yeah, linear regression is a method to predict a target variable by finding the best relationship between the dependent and the independent variables. And in regression, you you have one independent variable, but in multiple linear regression, you have more than one independent variable. Again, another snippet from the R code, and as we can see, this is the RMSE value to 107. That's a good value. And then decision tree, that's the second model. And it again, it builds regression of classification models, basically in a tree structure. What decision tree does is it divides the data set into smaller and smaller subsets into smaller trees until the data sets are pure, and then builds associated decision tree from there on incrementally. And final tree is again a tree with a node, a decision node and a leaf node. The RMSE value here is 2.19, another snippet from the R code. These are the various graphs from the decision tree model. That's one of the trees. This is the size of the tree compared with the CP values. Another tree that we make here. Moving on to SVM. So SVM is a supervised machine learning algorithm. Again, can be used for both classification or regression. And what it does, it basically looks at the data sets and draws a hyperplane that best separates the two classes, the two data sets. And so our main objective here is to find that hyperplane separating the two data sets, the two classes. Another snippet from the code. So here we can see the RMSE value is quite high, 2.45. Probably the least, I wouldn't say it was, but yeah, the least effective model out of the four, according to the RMSE values. Moving on to XGBoost, it's a recent, comparatively relatively recent model algorithm. So what it does is it's a boosting algorithm, and it builds a model from the training data set, and it tries to create another model which attempts to create the errors from the previous model. And again, it builds a number of decision tree and then averages out the prediction to give us the best fitting model. uh, Another snippet from the code. As you see, the RMSE value is the least of the lot, and yeah, so this is the conclusion. So the values vary a bit. So this is the one that I did yesterday, and uh, XGBoost has the least RMSE, so that's the best fitting along with linear regression, whereas decision tree and SVM are not that effective. And in the future work, I would also like to work a little more on SVM with different kernels and different implementations. And yeah, so that's my project, and let's just see if SVM is still running. All right, I'm just going to pause this and hope resume it when SVM runs. We can just go through the RMSE once and then we're done.